Good morning. Okay, so we are discussing the system of equations, and we had discussed last class. We had discussed how to find the solution of system of equations by using Gauss elimination approach, and we had also given some examples, two three examples we had discussed. Okay, whether the system has a unique solution or infinitely many solutions or no solutions by using these techniques. Okay, and also some of the properties of elementary properties of your determinant also we had discussed yesterday. And these are the problems we had discussed yesterday. Okay, find the quadratic equation of the form. Okay, these are the things we had discussed using Gauss elimination approach, right? And we have also given some problems. Okay, whether the system has infinitely many solutions or no solutions. All those things we had discussed using this Gauss elimination approach, and also the determinant properties we had discussed. Now we'll move further. We'll discuss about something about the rank of the matrix today. Am I audible to everyone?
Yes, sir.
Fine. So we'll discuss today the rank of a matrix. I'm going to, as I said earlier, there are many number of definitions, but we shall connect those definitions with the row reduced echelon form, row echelon form. Okay, so we'll first we have for any given matrix, we'll try to find the row echelon form, a row reduced echelon form. The number of non-zero rows in that row echelon form is called the rank of a matrix. Okay, so any matrix is given, A is a matrix is given. After row elementary operations, we have C matrix C, which is nothing but row echelon form, row echelon form or row reduced echelon form. Row echelon form or row reduced echelon form. Okay. So then in this matrix we will see that the number of non-zero rows. The number of non-zero rows. Okay. So we'll after using these row elementary operations, we'll see the number of non-zero rows in the row echelon form, which is nothing but that number is nothing but the rank of a matrix. Okay. So in the row reduced echelon form of A, and also the rank of a matrix will be unique because even you have a row echelon form or row reduced echelon form, both will be the number may not change. If you take a row echelon form or row reduced echelon form, suppose you have a matrix 3 by 3 matrix. By using a row echelon form, you are getting rank is 3, and then using row reduced echelon form also you will get a 3. So it doesn't matter that what you consider. So you consider either row echelon form or row reduced echelon form, so it doesn't matter. Okay, so that's what in the rank of a matrix we say that the number of non-zero rows in the row echelon form is called rank of a matrix. So sometimes this is called, because we are using a row elementary operation. So we sometimes it is called a row rank of a matrix. Okay, but the row rank of a matrix will be same as the column rank of a matrix. So you don't need to specifically find out a row rank and column rank, because the row rank of a matrix as well as the column rank of the matrix both will be same. Okay, the row rank will be equivalent to the column rank. So we don't need to find it separately, but because you are using a row elementary operation, so sometimes specifically some book they write row rank of a matrix, but of course that's not required. So you can directly write that rank of a matrix. Okay, sometimes some people refer it to row rank of a matrix. Row rank of a matrix, but this is equal to, always this is equal to column rank of a matrix, so it doesn't matter what you consider. One thing is that if you want to find out row rank of a matrix, I mean rank of a matrix, then you use row elementary operation. But if you want to find out a column rank of a matrix, then you use the column elementary operation. So whatever approach you do, so you do it for the column. Okay, so then it will give the same number. So that is nothing but your rank of a matrix. So row rank of a matrix will be same as column rank of a matrix. So which will be same as rank of a matrix. Okay. So it doesn't matter. So these are by these outlines we'll define it. Rank of any matrix A. Okay. The number of non-zero rows. The number of
Sir, are the ranks same even for matrices that are not square?
row rank and, yeah, row rank and column rank, that will be because we are talking about an m by n matrix. Okay, it doesn't mean that, okay, uh, uh, we are talking about a matrix of m by n only, so it means that it can be different. Okay, it's not always 3 by 3, 4 by 5, I mean square matrices. It is true for even a non-square matrices also. So we are talking about a matrix is A is an m by n. M and n are different matrices only. Yes, that result is true. Okay, so the number of non-zero rows, the number of non-zero rows, number of non-zero rows in the row reduced echelon form or row echelon form of a matrix A is called rank of a matrix. Rank of a matrix. Okay, so therefore, we'll have the, okay, some examples. Let us look at that. Look at some examples. Find the rank of a matrix. Find the rank of the matrix. Find the rank of the matrix. A is equal to 1, 2, 1, 1, 2, 3, 1, 2, 1, 1, 2, 1. Okay, find the rank of the matrix 1, 2, 1, 1, 2, 3, 1, 2, 1, 1, 2, 1. Okay, so now can you use the row elementary operations? Use the row elementary operations. Okay, use row elementary operations. Use row elementary operations. Elementary operations to get row echelon form. Row echelon form. Okay. So that is not difficult to see 1, 2, 1, 1, 2, 3, 1, 2, 1, 1, 2, 1. Okay. The first thing, okay, row elementary operation. So I'm just trying to use that 1, 1, 2, 1 is there. This can be subtracted with this, and this can be subtracted with this 2 minus 2 times of this. So then what I get? So 1, 2, 1, 1. I'm just getting 0, minus 1, or maybe this minus this. Okay, 2 times of that, that minus that, so this is minus 1, 0. Some may get positive also, but you can multiply with minus. And similarly this is 0, minus 1, 1, 0. Now again, you can add these two, you can add these two or subtract these two. So this will give us another thing. This will 1, 2, 1, 1. You can multiply by minus 0, 1, 1, 0, and then this is 0, 0, 2, 0, right? This is another operation. Okay, so you can add these two, r2 plus r3, you can add it, and then what else we can do it, you just see that. Okay, so now you can make this number also to be 0, or this number. Okay, you can subtract once again, r1 implies that r1 minus this. Okay, r1 minus r2, you can use that, make use of that. So this will give us something 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0. So now this first number non-zero is 1, non-zero is 1, non-zero is 1. So this is a row echelon form matrix. Okay, so therefore this is non-zero rows is 3. So therefore the rank is 3. Now you see this matrix. This is not a square matrix. Now you see that 1, 2, 3, 3 by 4 matrix, right? 3 by 4 matrix, we are getting a rank is 3. So can we now see the column matrix? Now we'll use the column operations. Now can we use column operations now?
Sir, we could have skipped the last step, right? I mean,
You
left
can,
it where.
you can, yeah, you can skip. It's not necessarily that you will be having that. Okay. So suppose somebody may get the different thing also, right? You could have skipped the last step also. That is correct. Only thing is that you make sure that that is a row echelon form. The form is not, form must be row echelon form. That's it. It is not that you should make always one. Okay. Yeah, that is okay. So you may get a different the matrix also, the final matrix. That's not a problem. Only thing is that you make sure that it is of row echelon form. Okay, for second matrix, I found a row and column also. So next, okay, so next matrix, let us look at is find the rank of a matrix. Find the rank of a matrix. Find a rank.
Sir, 2.
Yeah, good. The rank is 2. Correct. So the rank is 2. So suppose the elementary operation, I'm just writing it. You can just verify that. Okay. So you have 1, 2. Okay. So from that I can write directly. So from this, okay, first step, the second step would be, because you have 1 here, 1, so you can subtract directly R3 minus R1, or R1 minus R3. And similarly this one R2, and then R2 minus 2 times of R1 will give us the first iteration. So that will give us 1, 2, 1, 1, 1, and this is okay, 0, minus 1, you'll get minus 1, 0, 0, and then you'll get 0, minus 1, minus 1, 0, 0. Now these two are same, so you can subtract, okay, these two, so the last row will be 0. Okay, and then from this you will get, one can get, and sorry, this is 1, 2, 1, 1, 1, and this is 0, 1, 1, 0, 0, and this is 0, 0, 0, 0. Okay, further reduction is not possible. Okay, so therefore you can see that number of non-zero rows, and then the rank of the matrix A is 2. Okay, now let us look into the column operations also, because as I said, the both are same. Now we'll use the column operations. Okay, so now use the column operations. So we have a matrix A is, let us write the matrix once again. Okay, 1, 2, 1, 1, 1. Okay, 2, 3, 1, 2, 0. Sorry, 2, 2, 1, 0, 1, 1, 0, 1, 1. Now let us look at the column. So this is my column C1, this is my column C2, this is C3, and then C4, and then C5. So let us look at the C4 and C3, both are same. Okay, C4 and C5 both are same, so I can subtract easily. So these two will be, one will be 0, at least the last term will be 0, or the fourth column will be 0. So from this I can make one observation. This is nothing but, I can make one observation. So this is 1, 1, 2, 1, and this is 2, 3, 1, and this is 1, 1, 0, this is 1, 2, 1, and this is 0, 0, 0. So one column is 0. Okay, so one column is 0. So now you see that there is a 1 to 1 is here in this column, and then there is a 1 to 1 here in this column. So I can subtract this C2 minus, sorry, C4 implies that, C4 implies that C4 minus C1. So that will be direct, will give us one column 0, 1 to 1, 2, 3, 1, 1, 1, 0. So this is 0, 0, 0, 0, 0, 0. Okay. So now we shall see that what are the other possibilities we can have. Okay, so maybe what we can do, that this can be subtracted with this, because one is here, one is here, this can, we can make these two number to be 0. Okay, and here 2 minus 1 you will get 1, 3 minus 2 will get 1, so that these two columns can be subtracted. So from this again we will get, again we will get from this again you will get the final matrix. I'm just writing 1 to 1. So you will get 1, 1, 0, and 1, 1, 0 means this can be subtracted with this. This is the thing. So now further, maybe you can make this is 1 by 2, okay, and this you can divide by this one. This is 1 by 2 or something like that, or you can interchange these two. Okay, you can interchange these two. So the final matrix would be 1 1 0 1 2 1. Okay, then 0 0 0 0 0 0 0 0 0 0. So further reduction is not possible. So the number of the non-zero columns is here 2. Okay, so therefore the rank of a matrix is 2. So that will remain same. So you don't need to verify these things always. Just to clarify that these two numbers are always same for any matrix, whether it is a square matrix or rectangular matrix, so it is same. Okay, so and if you have any system of equations, that is the other observation, the rank of a matrix will always be less than or equal to the rank of augmented matrix. Okay, so that remark maybe we can just note down. It might be required for sometimes. You have a system of equations ax is equal to b. Okay, system of equations ax equal to b, and then we have a matrix a b. We denote this as an augmented matrix. Am I audible?
Yes, sir.
Okay. Okay, so AB is nothing but an augmented matrix. So this is the result or remark. So you can take any system and you can just verify this. Then the rank of matrix, rank of A, that number is always less than or equal to rank of augmented matrix. Okay, so this is one result we can have. So sometimes in terms of square matrices, we use some terminologies called a full rank. Full rank means suppose you consider any square matrix, let's say 3 by 3 matrix. If the rank is 3, then we say that is a full rank. Okay. So if that is the case, if A has a full rank, let's say any 3 by 3 matrix you'll get, if it is a full rank, then it will have a row reduced form is nothing but you will have an identity matrix. So that will be the one more remark or result we can say. So we can have this as a definition or note. Okay. So a square matrix or an n by n matrix. Okay. A n by n matrix A is said to be full rank. Is said to be full rank if rank of A equal to n. Okay, the number. Suppose you have a 3 by 3 matrix, the rank is 3, then you can have this thing. Okay, so you can have this result. Okay, so we'll see this as a result. Okay, so we'll say this as a result. Let A be a square matrix of order n. Let A be a square matrix of order n. Then the following statements are equivalent. The following statements are equivalent. Okay. First thing is that A is invertible. A is invertible. A is invertible. Second thing is that A has a full rank. A has a full rank. Third one is that the row reduced form of A. The row reduced form of A is IN, means identity matrix. Okay, so these three conditions are equivalent. Conditions are equal means what? One implies two, two implies three. Okay, if A is an invertible matrix means you know that inverse exists. Okay, so if A is an invertible matrix and then A has a full rank. Full rank means it has the rank. Let's say 3 by 3 matrix means it is a three. Rank is three. If that is so, then you will get a row reduced form is nothing but identity matrix. Identity matrix in case of 3 by 3 matrix, you know 1 0 0, and then you will get 0 1 0, and then you will get 0 0 1. Okay, so this is what your row reduced echelon form as well as an identity matrix. So these are the things are equivalent, so therefore 1 implies 2 is true, 2 implies 3 is also true, and then 3 implies 1 2 is also true. This is also true. If it is a row reduced form, then further reduction is not possible. Your rank will be 3, so in that case you will have an invertible matrices also. So these are the conditions one can make use of that. Okay. So if I want to say something is A has a full rank, then you can just see the row reduced form is nothing but an identity matrix, and then you see that it has an invertible. Then you can conclude that. Okay, so that is another way of saying that it has a full rank. Okay, that's okay. Full rank you don't need to separately find out. Sometimes for a square matrix, this result is true. And I think in the elementary level, we have also seen that based on the rank, also that the solution has been given, right? If you take a solution, system solution, a system of equations m by n, then there might be some of the thing is true. If rank of A is less than rank of augmented matrix, then the system has no solution. If rank of A and rank of A be same, but it has the system has a solution, but there are two way, and the rank is n is a unique solution, and then infinite number of solutions. So maybe we can state that as result, because system of equations will focus only on Gauss elimination method, so that we have done already. Okay, so we don't need to study separately by using this Cramer's rule, by using rank approach and all those things. We are strict with the system solution of a system of equation only by Gauss elimination approach. Okay, let us maybe state this result. Okay, because we'll just recall those results which we know already. Okay, we'll just recall this result. Am I audible to everyone?
Yes, sir.
Okay. Suppose we have a system of equation. Suppose we have a system of equations. Suppose we have system of equations. Ax is equal to b, where A equal to m by n matrix. Okay, it can be a square matrix also. That is not a problem. That's not a problem. Then you can say that then exactly one of the following statement holds. Then exactly one of the following statements one of the following statements holds. Okay, so as I said, the rank. Okay, based on the rank we are going to write. Okay, the first case, if rank of A if rank of A is less than rank of augmented matrix. Rank of A is less than length of the rank of the augmented matrix. So okay, suppose the rank of A is, let's say, 2, but the rank of AB is nothing but 3 in case of 3 by 3 matrix. So then in that case the system has no solution. Then the system has no solution. Okay, so if rank of A is equal to rank of A, less than rank of AB, then the system has no solution. So now second case is that obviously which is equal, right? If it is equal, so the second case, rank of A equal rank of AB, then the system is consistent, but it has the following two more things. Okay, then the system,
Sir, you have written A is M cross N matrix. It should be square, right?
hmm,
Sir, you have written A is M cross N matrix.
M cross n, it's not a square matrix, na? It is true for in. Okay,
So we can have like four variables and 5 equations like that also.
yeah, like that also, because we are talking about in general only. In generally we'll give in terms, because we are talking about with respect to rank, na? Rank can be fine for any matrices. That is not an issue. Because the size is m by n, the size is m by n, but nowhere we say that it is strict, because to give a counter example we strict with the square matrix. Okay, to give a counter example we strict with the square matrix, because square matrices are very simpler to handle. So if rank of A equal to rank of AB, then the system is consistent. Okay, then the system is consistent. Furthermore, we have two things. We'll have the solution, no, unique solution and infinitely many solution. Furthermore, okay, so the first case I would say, okay, rank of A equal to rank of AB. Let us say that the given number is, the maximum number will be, okay, m by n. So the maximum will be this n only. Okay, m by n. Okay, so m by n, in that case, if the rank is n, then the system will have a unique solution. If the number is less than n, then it may have an infinite number of solutions. So this is true in general. So this is true for m by n matrices also, as well as n by n matrices also, square matrices also. Okay, if rank is n, if rank of A is equal to n, so that means rank of A, rank of AB both will be same. Okay, both will be same. Then the system, then Ax is equal to B, Ax is equal to B has a unique solution. As a unique solution. So, and other thing is that it might be less than n also. Let's say it's 3 by 3 means you can have a 2, you can have 1. That is the maximum possibilities. You cannot have 4. If you take a 3 by 3 matrix, so that is the reason we don't consider the greater than conditions. Okay, either it can have rank of A is 3, and then it may be 2, it may be 1. So if it is equal to the given number, then it will be a unique solution. It will be less than that, it will be an infinite number of solutions. So if rank of A is less than n, if rank of A is less than n, then the system has an infinite number of solutions. Has an infinite number of solutions. Has an infinite number of solutions. Okay, so this is the other observations. We can just make it out, and one can give a counter example for that. You can take any examples, any system you take, and then try to find out the solution of that, and you will get you know based on the rank you can just do that. Okay, so above examples also you can take. We have discussed some of the examples, I guess. Those examples that by Gauss elimination approach, we have some examples. That same example if you take, suppose you take this example. Suppose let us take this example number 2. Okay, suppose you have a this, and then we are writing with respect to an augmented matrix. So of course there are elementary operations, so now we are trying to find out final matrices. But now further we have to do some more reduction, so because you have to make this to be 1 and this to be 1, so you can have this is divided by 3. So this is 1 by 3, this is 2 by 3, this is 1 by 3, and this is 0, this is 1 minus 1, this is 0 0 0, and then you this will be also changed. Okay, so in that case, you can see that rank of A is 2, but rank of AB is 3, because AB is involves these column, this row also. 0 0 0 6 is also there, and then 0 1 minus 1 6 is there, and then so therefore this is rank of A is 3 2, but rank of AB is 3. So these two are not same. So this is the solution is not possible. I mean, the no solution exists. The system will have no solution. So the same thing you can have for this problem also. It has an infinite number of solutions. Okay, you can see this. See, rank of A is also 3, sorry, 2, because the number of non-zero row is 2. And similarly, in B column also you have a 0 here. So the rank of AB is also 2. But the given matrix is 3 by 3. So therefore, one number is less than. Okay. So the rank of rank of AB is 2, but not 3. So then in that case, you can have an infinite number of solutions. So in similar way, you can just make use of all those things. One can conclude those things. Okay, so if you have a rank of A is less than of rank of A, then you have a no solution. If it is same, then you see that whether that rank is given number, that is then the system has a unique solution. If it is less than n, then the system will have an infinite number of solutions. Okay, so by this thing we can just find up this matrix quotient, and this is an elementary matrix algebra. We can just find up, and we can move to the formal core linear algebra. So before we talk about an vector space, and let us now first define that field. Okay, field is nothing but you take any two numbers. Okay, you take any two numbers in the real line. Okay, you take any two number, real line represent these lines, just simple line. Okay, so this is -3, -3, -2, -1, 0, 1, 2, etc. And this is also etc. Right? This is -3 here, -2, -1, 0, 1, 2, etc. This represents just simply the real line. You take any two numbers. Okay, if I take any two numbers, let's say 0 and 1, so their addition is possible, the subtraction is possible, associative property is positive, and you can have an inverse number, you can have commutative property, you can have associative property with respect to addition, with respect to multiplication, and then with respect to you can have also have distribution over the addition. All those things will be true. I mean, if you take any two number, let us take x comma y. Am I audible to everyone?
Yes, sir. Yes, sir, you are audible.
Fine. So if you take any two number x and y, so their addition is possible. X plus y is also possible, and x into y is also possible. And based on these two operations, one is that plus, and the other is that okay. If you put dot, that is a multiplication, and these operations plus and dot, under these two operations, it will satisfy certain things. I mean, once again, we are going to discuss x plus y is equal to y plus x is equal to yx, x plus y plus z is same as x plus y plus z. I mean, all those properties will be true. If all those properties are true, then you can say that whatever you take, that is nothing but a field. Okay, that is nothing but a field. A field will satisfy certain properties with respect to those two operations. One is called addition, and addition as well as the multiplication. Okay, with respect to those properties, we can state some properties which are called a field. Of course, that this R can be R can be further maybe extended to the complex number system also. Complex number is will be little bit higher because you are going to talk about a plane. Complex number means that can be represented in R2. That can be represented R2 because you are going to talk about the two numbers. In complex number means that is nothing but represented z equal to x plus iota y. So that is nothing but you can represent that as an Argand diagram. So that will be a different approach. You can have field means it can be either real number or complex number because both will satisfy all those conditions. Okay, real numbers means that will represent just a number minus 1 1 2 3. Complex numbers means that will be something like that 1 plus I0 1 plus 1 2 I something like that, but both will be a field. Okay, so we'll stick with we'll say f whenever we are dealing with some real number, but mostly we'll be dealing with a real number only. We don't go to the complex number. Rarely we may access complex numbers, but we morely focused on only the real number system. We don't extend further. So let me state the definition of a field. Then tomorrow we shall discuss. Coming class we'll discuss that. Okay, let me state the definition. Okay, so let f denotes the either set of real numbers or complex numbers which will satisfy the following properties. Let f denotes. We say that let f denote let f denote either the set of real numbers the set of real numbers or the set of complex numbers or the set of complex numbers which will satisfy the following properties. Okay, so we're going to just see that. Okay, f denotes the set of. So one is that we okay under the two operations addition and multiplication. We just write that as that. Okay, first property. First property. So x plus y is always same as y plus x. So any two number you take, these two are always true. X plus y, 1 plus 2 will be same as 2 plus 1. That is true, right? For every x comma y, for every x comma y in f. Okay, and then second property. Okay, x plus y plus z. If you add these separately, and this is same as x plus y plus z. This is once again true. Okay, for all x comma y comma z in f. Okay, this is once again true. And then real number 0 is exist. Okay, so there is a number 0 in such that x plus 0 is also okay, x plus 0 is x for every x in f. Okay, because the 0 is there in the real line, so this is possible. And for every real number there is a negative number also there. Okay, for each x, for every x, okay, for each x there is a minus x. Okay, such that x plus minus x is also there. If you add 1, then minus 1 is also there. Okay, so this is also once again in f. So these are the four properties. Maybe I would say that with respect to addition, similar thing we can have with respect to multiplication. Okay, with respect to multiplication, we can have the commutative property xy is equal to xy is equal to yx, and then for all x comma y is in F. Okay, and similarly x into yz will be same as xy into z. Okay, x into yz will be same as xy into s. So this is once again true for all values of x comma y comma z in F. Okay, and similarly here that because we are dealing with respect to the multiplication, so therefore for each value of 1, okay, there is a unique non-zero element 1 in F. Okay, such that, so this is also true, 1 into x is equal to x, which is again in F. Okay, so this is also true for all values of x. And whatever value you take, suppose I take, because we are talking about a real number system, so suppose you take a real number, so suppose 1 by 2 is there, 2 is there, then 1 by 2 is also there, because that is nothing but a rational number. Okay, so therefore if I have a 3 is there, then 1 by 3 also there, because in the real number involves everything, right? So therefore for each x, or you can say that for each x, there is an 1 by x. Okay, such that x into 1 by x is also there, 1 again, because x gets cancelled, this is also there. And the last property, addition and multiplication both can be combined together, so that is nothing but x into y plus z. Okay, xy plus yz, this is true for all values of x, y, z in F. Okay, so therefore if I want to say something is field, so it should satisfy all these 9 properties. Okay, it will be automatically, whenever I say the real number is a field, the real number means the real number will satisfy all these conditions. As I said earlier, you're talking about a real number system, so real number system, whatever number you take, all those numbers will be satisfied. Okay, so you take addition of those two numbers, and then you have a multiplication of those two numbers. If you take -1 and 1 is also there, then their addition is 0, once again that is there. And you take 1, and then 1 by 2 is also there, because in between this 0 and 1, 1 by 2 is there. And similarly if you add 2, 1 by 2 is there. So all those things are there. Okay, so therefore it forms a field, and this is a precise definition of a field. So if you want to say it's a field, then it will satisfy certain things. Okay, so there are some examples also you can take, which may not be this also. Okay, field also, because you take a set of positive integers, may not form a field, because you take you are talking about only the positive numbers 1, 2, 3, etc. So therefore -1, -2 are not there, so in that case that will not form a field. Okay, so you can have those are called of course it may not be a subfield also. Subfield means it will satisfy at least some of the conditions. So okay, so those are not you can give a counter example for that also. Okay, some particular subset of R you take, sometimes it may have it may or it may not be a field. Okay, some particular subset, okay, some particular subset you take, then it may have or it may not have also. So in some of the standard books, of course, in whenever we are discussing about the system of equations, we have not spoken about the field, because that I have spoken without talking about the field of real numbers or field of something. But there we are talking about the real numbers only. So we are considering all those numbers are real. So those things are actually is connected to the field only, because all those entries are field. Okay, all those entries x1, x2, all those solutions are is also field only. Okay, so that is somehow that is connected with your this one real field. So by using this field, okay, if you want to say something is a vector space, so vector space, first of all, it should be over the it should be a it should be a field. Okay, first of all you have to consider the whatever the scalar you consider, all those scalars must be in field. Okay, so and then we say the set of objects V, and again it will satisfy certain properties, similar properties like a field. Then one would say that that is a vector space, and then based on those properties, and then we can discuss further. Of course we don't discuss much on vector space, but the properties is derived from the vector space. Those things are very important. Okay, so we are going to once we talk about a vector space, then we'll be speaking about something is called a subspace. Subspace means it doesn't satisfy all those properties, but at least some few properties will satisfy. And once you have the subspace, then we'll go come back to the basis and dimension. You have a basis and dimension, then you can have a linearly independence and linearly dependence, and all those concepts will come after that. Okay, so maybe in next class we shall discuss that.
Sir, in point number 8, x not equal to 0 is necessary, right?
Yeah.
Because
Because that 1 by x is there, na? Yeah, x not equal to 0. For every x not equal to 0. Yeah. Thank you. X not equal to 0 is required. Otherwise, 1 by x may not exist, na? So and one more thing, that we are having 4 lectures per week. Whenever we finish some of the topics, we can have a problem session. Okay. So in that case, you can have. I will give some problems. You can do that practice. Like you can do that within 1 hour only. Whatever you can do it. Okay. So maybe by Monday we can have a problem session. Monday we can have a problems from row echelon form, row reduced echelon form, rank of a matrix, and Gauss elimination method. Monday class. So every week at least, whenever we finish some of the things, and we can have a kind of a problem session. So that would be good. That would be good for you. Okay, you can have a practice. I'll come up with some problems, and then you try to find out and just tell us the solutions. If there is some doubts, we can have a discussion there. Is that all right?
Sir, the point number 9, sir.
What is that?
Sir, point number 9, it will be xy plus xz, I think.
Xy plus. Oh, sorry. Yes. I'm just multiplying inside. Yeah, correct. So xy plus xz. Sorry. Thank you. I'm just multiplying that. So something like that we'll do weekly once. Whenever we complete, we feel like okay, we have discussed some of the things. We can have a discussion, and I'll try to make one some of the this one assignment sheets also. Then I'll put it in Google Classroom, so you can access and you can do the practice problems. That is also we'll do it. That is there will give a more number of problems. Maybe in class time we'll give 3-4 problems, so that you can try. And then in tutorial sheet I'll give more problems. You don't need to submit the tutorial sheet, just for your practice. Okay, so I'll put some problems in the Google Classroom also. I'll add all of you in Google Classroom, so that all those lectures notes and all these tutorial sheets will be posted there. You can access from there. So any questions from today's lecture?
sir, is vector spaces also in course?
Yeah. So whatever we had discussed till last 3 classes, those things are in course only. So whatever I'm going to discuss, all those things are in the course only. I'm not discussing anything out of the thing. Okay. So syllabus, maybe if you want, I've already written the syllabus. Those things are the syllabus, but anyway, that it can be seen from the book also. I'll see that. Okay, I'll see and I'll share it that. So that would be useful for you also. Vector space is the core. That is, without that we are not going to do anything. Vector space is the core. And the syllabus starts from your this only, rank of a matrix, system of equations, Gauss elimination method, and all these things are there in the syllabus. That is the elementary thing, but that is also included in the syllabus. So we'll be included that also. Okay, Gauss elimination method, rank of a matrix, all these row echelon form also there in the syllabus. So I think you can leave. There are no questions.